This is a video on token and text-based multimodal models with a focus on text-to-speech. I'll be covering the CSM-1B text-to-speech model, also the Orpheus text-to-speech model, and I'll describe Moshi, which allows for speech-to-speech conversations. Now, Llama 4 is not released when I'm recording this, but it's about to be released within a month or two, and it's said to be a multimodal model that natively supports audio and text. The way it does this is likely by assigning tokens to the audio in the same way that we tokenize text, and this allows you to use a transformer to process everything in a very consistent and simple type of architecture. So these text-to-speech models that are token-based have already emerged. They're available now. They provide very good quality speech, and they also allow you to do voice cloning and even fine-tuning. I'm going to cover all of that in detail in code. But first, let me describe a bit more how these token-based models differ from some of the traditional approaches to text-to-speech. Now, with end-to-end multimodal models, ideally, you would like a few things. You want to take in and produce text and audio. You want to be able to do those in any kinds of combinations. If you can do that, your model is in principle a text-to-speech model, a speech-to-speech model, a text-to-text model, and a text-to-speech model. You'd also like to cover emotion. So you don't just want to cover the fact that there are words being spoken, but you want the output, the model's response, to reflect and respond to the emotions that are there in the input. Now, you'd ideally even like to be able to cover cases like silence or music, so that regardless of the inputs that are going into the model, you could just think of turning on your phone and your microphone. The model would produce an output that's corresponding to that. So if you just have your phone listening to the background and there's nothing happening, your phone should not be speaking. But then if you start speaking to it, it should then start responding. And this is kind of behavior you do see with Moshi, which was released last year. It is an end-to-end multimodal model. And this is something that probably is going to be, it is going to be included in Llama 4 because Mark Zuckerberg has said that it would be. And with that, if you can cover these broad cases, you should also be able to cover arbitrary numbers of speakers. So even if you have two speakers and they're overlapping and some of it is noisy, the model should be able to deal with that, much in the same way that when I'm listening to noise, sometimes I just don't hear anything, but sometimes I can pick out one speaker or another speaker and respond accordingly. Now, for this section of the video, I'm going to describe the previous approaches for end-to-end models, which typically involves taking a Llama model or a Qwen model and tacking on an adapter at the start and then one at the end. And these work pretty well, but they don't allow for, say, emotion detection and response, for example, and they're not as general and the architectures get a bit more complicated. I'll also talk a bit about the current approaches for text-to-speech, notably diffusion type approaches, which I covered in the Style TTS 2 video. Then I'll start to cover token-based approaches and describe what the advantages are if you move towards a token-based approach. Basically, your architecture simplifies a lot. You can just have a transformer in the middle. Everything is a token. It goes in as a token, you predict new tokens, and then you just convert the tokens back to the audio using a decoder. Then I'll go through in detail the Orpheus release, which is a 3 billion parameter model based on Llama 3B. And then I'll cover CSM-1B. And for CSM-1B, actually I have this backwards here. For CSM-1B, I'm going to cover inference and cloning. And for Orpheus, I'm going to also cover fine-tuning. Which is pretty nice because it allows you to then create assistants that have very specific voice tones. I'm going to train it on my own voice, so we'll have an assistant that sounds like me, like Ronan. So let's take a look here at the previous approaches for end-to-end before I move on to the token-based approaches. And the easiest way to do this is to look at one or two papers. Two relevant papers that come to mind are the Qwen Audio and the Llama 3 paper. Qwen Audio is a multimodal model. It's partially multimodal, takes in speech, but also can take in audio. So you have a traditional transformer model that predicts the next token, but on the input side, you're able to input not just text tokens, but also audio inputs. And the way this works is by taking a speech pattern, converting it to a MEL spectrogram, which is kind of a frequency decomposition that's suitable for the human ear. And then you add in some MLPs. So these are multi-layer perceptrons, neural nets that are fully connected, and these transform the audio into a format that's compatible with the input here to the Qwen model. So you're not converting the audio into tokens per se, you're converting them into continuous embeddings, vectors, that are going to be compatible and understood by Qwen LM, at least after you've gone through some fine-tuning then of the whole model together. This model does not produce any outputs, and it does not have a distinct vocabulary of tokens for the audio input. So it can detect potentially some levels of emotion. I don't think, it can detect some emotion, but it's not able to respond in terms of text. It's not able to produce any output audio tokens. Now, in principle, the Llama 3 model goes further than this. Now, Llama 3 has been released at this time. It was released over half a year ago, but they did not release the audio part of the model. I don't know why that is. Maybe they deemed the quality not high enough. Maybe there are safety reasons. If there were safety reasons, though, why would they release it in Llama 4? So I just don't know why. But in principle, Llama 3 supported taking in audio and also creating audio. But again, the Llama 3 model does not have tokens to represent the audio. It uses an adapter, which, by the way, can also be a fine-tune of a Whisper model, which is quite small and converts from speech to text. One of the issues, though, with Whisper models is that they're designed for transcribing into text, so they don't care about emotions, and that means if you start with the base model, it's not going to be a great adapter for emotion. It's kind of an aside, but my point here is that the Llama 3 model supports audio, and it does so by tacking on an adapter at the front, and then by tacking on a speech generation model here. It's actually not described even what this speech generation model is. It's said to be proprietary if you read through the section here. But what's clear is that there isn't a set of tokens representing the input audio. There isn't a set of tokens representing the output audio. And so you don't have one unified architecture. You have a cobbled together overall model that has kind of the text inputs, the audio inputs that are converted via adapter, then text outputs, and then a way to convert into some audio representations on the output. So these are some of the traditional approaches, and we can contrast that now to the token-based approaches that are seen in Moshi from last year, then CSM-1B, and then in Orpheus. Now, a token-based approach, you'll hopefully be familiar with this for language models, involves taking in some tokens. So first you have a phrase, say the quick, you split it into subwords, and then that's your vocabulary. The original, or Llama 2, I think had a vocab of 32,000. Llama 3 had over 120,000. I think Llama's got a vocab of maybe 400 or 200, more than 200,000 tokens. But this is a fixed vocabulary of tokens that your text is split into. And then the model works to take in tokens and generate the next predicted token. In this case here, brown. Let me maximize my screen. Then you would pass that prediction back and predict the next token again, pass it back and predict the next token again. So this is a language-based model, and it's kind of obvious to see how you can start with some language and split that into a vocabulary of tokens. A very simple vocab could be just defining it according to letters. So you have 26 letters in your vocab, but then you can also use subwords, which allows you to represent a phrase of fixed length with less tokens if each token can cover multiple letters. So this is text-based. But what we want to do is move towards a model that can also support audio. So we want to have some audio that can be represented in the form of tokens, and we want to be able to auto-regressively predict the next token like this here. So the question is, how do you make tokens for audio? How do you convert from some kind of an audio wave into a representation that's captured by tokens? And what does it even mean to have a token for audio? Because it's clear in text a token is kind of a subword, but what's the analogy for audio? And the answer is you need to define a dictionary, or sometimes called a code book. It's a fixed number of vectors. These vectors are higher dimensional. I'm showing 2D vectors, but you can think of maybe 1000D or 500 dimensional vectors. And you have a fixed number of these. So when you represent the audio, you're not representing it with a continuous set of options. You only have discrete options like here, here, here. Another word is quantized. So you only have quantized options for the audio. That's what tokenization really means. It means quantizing the problem, giving the representations fixed values that are quantized, they're distinct, they're separate, as opposed to giving it a continuous representation. So you have this code book of audio tokens. It's a fixed set of vectors. As I said, for example, maybe 4,000 different vectors. And the way you create this code book, the way you decide which vectors should be included, so which directors to include, is with a setup like this here, and I'll go through it. And this setup is designed to optimize the following problem. You take an audio sample. This will be from a large audio data set. You pass it through a neural net, maybe a convolutional neural net, and it will create a representation here in tokens. So here we've decided we're going to represent with 6 of these tokens. They're all drawing from the same vocabulary. And once these tokens are created, we're going to put them through another neural net, which will go the reverse direction and convert it back into an audio wave. So I really could, show this here as being converted back into an audio wave. And what we want to do is optimize this setup so that the definition of these tokens, the definition rather of the codebook here, and the predictions being made by the encoder and by the decoder lead to a very good match. We want a very good match between this output and this input here. So we're squashing this down into a token representation. We're expanding it back into a voice representation. And we're asking the question, does the output match the input? And if the output does not match the input, we will back propagate in this direction here through these weights and through the definitions of the codebook in order to update everything and try to optimize not just this network here, but try to choose the codebooks in a way that are going to lead to optimal representation of this wave and indeed of any wave within the database as a set of tokens here representing the audio. So this is how we come up with the codebook representation. And once we have this, we're able to now do the autoregressive problem of passing in, say, the first number of tokens here. We pass in, say, 1, 2, 3, and then we're hopefully able to predict up here the next token. Sorry, I should copy both pieces. We're able to predict the next token here. And once that's predicted, we pass that down here. And then we go on and we predict the following one, this one here. That's maybe not the clearest way to show it, but you'll hopefully understand that I'm doing the analogous thing as with text, but now doing it with my discrete audio tokens. Okay, so this is how we train the encoder, the decoder, the codebooks. And now I need to talk about a problem with speech that is not so much there with text. So with text, when I'm talking as I am now, I'm talking probably at about maybe 2 to 3 words per second. And that means in order to represent my speech in real time, you need to be able to produce roughly maybe 3 tokens per second, which is not a very high rate of token generation. So it's fairly easy to keep up with my speech in terms of token generation from a language model. Now for audio, it's more difficult because when you just represent an audio signal using a single layer of tokens like this with one token, say, let's say you've got 12.5 tokens per second. That's a frequency of 12.5, which is what Moshi uses. It turns out that just having one layer of tokens does not give a very good quality sound output. So when you try and do this with just one layer representation, so that's one token for each segment of audio, this turns out to give poor representation. And so a solution to this is instead of just having one token for every segment, you have 2 tokens. And you can think of it as hierarchical. So the first token or the first codebook of tokens that it's drawing from, it represents some high-level attributes of my speech at this segment. But then maybe this one here goes a bit granular for my specific Irish accent, for example. And you could go even further and have multiple layers of hierarchy. In Moshi, there are 8 layers. In CSM-1B, I think there are 32 layers, or maybe that's Orpheus. But you can add more hierarchy, and this allows you to get really good quality in the representation of the speech. However, the problem is once you have more of these layers of hierarchy, that means you need to produce more tokens per second. And we can do a little calculation on this. If you take, say, Moshi, and you've got segments sampled at 12.5 hertz, you've got 8 tokens used per segment, so you've got 8 codebooks. To keep up with real-time speech, you need to do 12.5 times 8, so you need 100 tokens per second to keep up with the representation of my speech. Now, this means this is a pretty high rate of generation. For example, that's higher than even like Claude Sonnet. If you hit the API, or GPT-4o, maybe is at 80, maybe close to 100 sometimes. But you're basically forced to move towards smaller transformer models if you want to have the token generation speed to keep up with real-time audio. So this means that a lot of the models we see now that take the token-based approach, like Moshi, like CSM-1B, like the Orpheus model, they have small transformer models like Llama 1B, like Llama 3B. So Moshi is based on actually a 7B architecture, although they pre-trained their own transformer. CSM-1B is based on Llama 1B. Orpheus is based on Llama 3B. So because you have to generate this hierarchy of tokens, you've got to generate a lot of tokens per second, which kind of moves you towards a smaller model. So it'll be interesting with Llama 4, if we have the large models, will they just take the same approach? Because that could make them quite slow for speech generation and speech processing. Or will they find some tricks? And I'll describe a few of those tricks that have been found by Orpheus and by Moshi and by CSM from Sesame Labs. Now, what can you do with tokens that you can't do if you're taking, say, style TTS diffusion models, or say doing the adapter type approach? Well, you have a much simpler architecture with a transformer. You just put in these tokens and you get out the next token. And you pretty much have one main transformer that does this instead of having a complicated setup like in the style TTS2 paper. Actually, I'll show you very quickly how style TTS2 diffusion works. You would take in a reference snippet of voice. This is for cloning. You take your input text. You convert the text into phonemes, which is kind of an audio representation of how it's pronounced. Then you diffuse out a style vector. This is done using a diffusion model, like say stable diffusion. And you take that style vector and you take the acoustic phoneme encoder. So this represents the acoustics of the text here. And you combine them to go through a convolutional neural net, to generate your sound. And this is even a simplified representation. If you look at the detailed representation, and you can check out my video on style TTS2, this is a very complicated type of architecture that requires you to parse different things like the style, like the pitch, aligning the text. There are a lot of working pieces, whereas if you can do a transformer approach, you end up just having kind of this one transformer, and then you have tokens that can represent text or audio. So this is one of the big benefits of going towards tokens. The other thing that's a nice attribute is the tokens are able to capture pretty much anything. When you train the codebook, you can train it on a mixture of noise and speech. You can train it on a mixture of music and speech, so it can capture anything. You can even capture multi-speaker type patterns or multi-instrument type patterns. And even further, you can start, if you want to build a model like Moshi or you want to build a model like CSM-1B, and this is what they did for CSM-1B and for Orpheus, you can start with Llama as a backbone. So you can basically get big acceleration in your training. Start with Llama here as your transformer, or rather if I show it for audio, start here, and then start to train on speech using your audio tokens. So the token-based approach is pretty elegant. I expect this is what Llama 4B is going to do, and it allows for models that are just quite a bit more unified and quite a bit more general. So with that all done, I'm going to go through a quick overview of the Moshi architecture, then CSM-1B, then Orpheus. That won't take me long. And then I'm going to go through Orpheus Inference and Cloning. So I'll go through scripts here, showing you exactly how to run it on your Mac actually, or on a CPU. And then I'm going to run on a GPU to show you inference, cloning, and fine-tuning of the Orpheus model. And I have this one backwards here because I had it backwards earlier. So CSM-1B. Okay, so let's take a quick look at Moshi. And the Moshi paper is right here. And the two things I want to show you, I'll refer back to my presentation, are I'll show you how Moshi defines these code books, or how it sets up its encoder and decoder, which is called Mimi, by the way. And the same architecture is used in CSM-1B by Sesame for encoding and decoding. And then I'll show you how Moshi sets up its transformer. So how does Moshi set this up here, although it's audio and text tokens? So first, let's take a look at Mimi, which is the Moshi version of encoding decoding. And you can see that here, and it looks quite a bit more complicated. But if you zoom out, here is the input speech. It's going through an encoder. Here is the representation in terms of code books. Then you've got the decoder, and then you've got the output speech. And the whole goal of this thing called Mimi is to match the input with output and to backpropagate if that is not matching. Now, the encoder itself is not just a convolutional neural net. Moshi actually uses a transformer within the encoder and also within the decoder as well. So a little bit more complicated of an architecture for the encoder and for the decoder here. Now, in the middle, Moshi does not just use one codebook. So I've just got one codebook here. Moshi uses 8. And actually, these are split. So there's a set of 7 codebooks that represent the acoustics, and there's one codebook, which you can think of its own vocabulary, that's focused on the semantics. And this codebook is trained in order to align with the meaning of the input acoustic, of the input sound wave, as defined by WaveLM. WaveLM is a model that converts acoustics into vectors that correspond to the meaning of those input audios. So by aligning this here being the codebook for semantics, we're able to get a representation and a codebook that represents semantics. And then these all end up being aligned effectively by just aligning the output audio with the input audio by flowing through this encoder-decoder network. Now, I think Moshi tried just to use a straightforward 8 set of codebooks, hierarchical codebooks, but they found that this wasn't representing the semantics so well, and that's why they decided to split off and have one codebook dedicated towards the semantics. So this is Mimi, this is the encoder-decoder and how they define codebooks. And then we can take a look at the diagram here for how the transformer works. So here's the transformer setup. You can see the audio comes in here to Mimi and gets converted into tokens. So these are audio tokens. These audio tokens go into a transformer, and this transformer basically predicts the next audio token, and that gets sent back to the front, and you keep predicting new audio tokens, and then those tokens are converted back to speech. Now, actually, this transformer does not strictly calculate the next audio token. What it does, and why does it not? It does not do that because of this problem I described, whereby when you move to having the hierarchical description, and remember Moshi has got 8 layers here, you end up needing to create a lot of tokens at every time step. And so what Moshi does is, rather than predict all of the hierarchy, which would be 8 tokens here at every time step, Moshi instead predicts an embedding at each time step. So predicts a big vector that represents the next time step. So here, the output of the transformer is not actually the next audio token or the next 8 tokens. It's an embedding. And that embedding is then used in a second transformer that's much smaller, a depth transformer. And that depth transformer then generates the 8 specific tokens. So yeah, there's a layer of hierarchy here in how the tokens are defined. And then there's a hierarchy of transformers. There's a big transformer that produces an embedding. And that embedding is used by a smaller transformer to then decode the 8 different tokens for that time step. And then you go back again and you create the next embedding and you go around again. So by adding this hierarchy, it means that now Moshi only needs to produce one big embedding per time step, and then using a smaller model, it creates the 8 tokens. So it allows you to create more tokens per second. And Moshi uses a fairly big transformer. It's 7 or 8 billion parameters. It was pre-trained by Moshi, and it's actually a really high quality model that was competitive at the time it was released. It's kind of surprising they went to the trouble to train this, but at the time, apparently there weren't models that were permissively licensed. Llama, I think, was forcing the models to have the word Llama within it, and so they chose to pre-train the model. This is in contrast to Sesame and to Canopy Labs with their CSM-1B and Orpheus models, where they just used off-the-shelf 1B, Llama 1B and 3B models, benefiting from the more open license on the Llama 3 model versus Llama 2. So this is Moshi. Let's now take a look at what Sesame do with the CSM-1B model. So they take in as well, they can take in text and audio. They can actually take in prior conversations, text and audio, in order to better inform the shape of the audio that's being converted, or the shape of the audio that's being generated from text. This is a text-to-speech model. And just to say that again, if you want to convert text into speech, you can also input prior conversation so that the text sounds like the prior conversation when converted to audio. Now here's the transformer. It takes in tokens. It auto-regressively produces the next token. But like with Moshi, rather than trying to produce the full hierarchy at a given time step, the model in CSM-1B does not do that. But it also does not create the next embedding like Moshi does. Rather, it decodes the first token in a series of 32. So CSM-1B uses Mimi, but it uses it with a number of codebooks of 32. And furthermore, it uses the big transformer to predict the first of those codebooks, the highest in the hierarchy. And then it uses a smaller decoder to decode out the other 31. So again, it's using hierarchical transformers, a big one to create the first token, and then a smaller one to decode out more precision into the audio here. So again, this gets around the problem of needing to generate too many tokens in order to keep up with real-time speech by having a big transformer and then having a smaller one here. Now, the last model to cover is Orpheus. Both of these models came out at a very similar time. Sesame's model is based on 1B Llama. Orpheus is based on 3B, both Llama 3. And Canopy Labs, with their Orpheus model, rather than having 32 codebooks, they actually use a single codebook. Well, you can think of it as a codebook, a single set of audio tokens across all of the hierarchies. But what they do is they build up a convolutional neural net that creates some tokens to represent a first level of decoding. So they'll decode, or rather they'll encode the audio into a first set of tokens, and then they will further encode it through more convolutional neural net layers into a second set of tokens taken from the same vocab, and then they will do that again. And I think there are 4 layers of hierarchy that are represented. So this Orpheus model will also use hierarchy to define its audio, but the codebook, the set of tokens, is the same for each layer. It's just that those layers are generated at different degrees of depth into the convolutional neural net. And when decoding, you go in the reverse direction. So you'll decode from your most granular tokens into more coarse, more coarse, more coarse. Now, this model here, the Canopy Labs model, it does not use 2 transformers. It just uses 1 transformer. It actually flattens the sequence of tokens here, so they're all sequential. This means that when it wants to decode, it's literally going to decode this token using the transformer, and the next token that will come out will be this one, the next one will be this one. So the same transformer is being used to decode all of the tokens for a given time step, which means you need a small transformer because otherwise your process is going to be a bit too slow. So I haven't looked in detail actually at the speeds of decoding, but my guess is that Sesame is faster, both because it's a 1B instead of 3B, but also because Sesame uses hierarchical transformers, so it's using a smaller transformer for decoding, whereas Canopy Labs is using just 1 transformer to do pretty much everything. Okay, so that is that for the explanation. I'm now going to move to going through the scripts for CSM-1B, and then I'll go through the scripts for Orpheus, including all the way towards data generation and fine-tuning. Next, I'm going to take you through inference and cloning for the CSM-1B model. Then I'll take you through inference, cloning, and fine-tuning for the Orpheus model. And actually, I'll do a combination of fine-tuning and cloning with the Orpheus model, which combined tends to give really good results. All of the scripts are in advanced transcription. If you'd like to get access, you can purchase that on trellis.com/advanced-transcription. Now, I will try to describe everything in detail so that you could build it by yourself, and I'll also provide the links to the original repos from CSM-1B and the original repo for Orpheus, which have scripts as well that you can work through. So I've cloned this repo into Cursor, and I'm going to show you how to run the the CSM-1B model on a Mac. You could actually run either of the models on a Mac because they're quite small. You could even run it on a CPU. And I'm going to run the Orpheus model then on a GPU, just to show you the comparison. I'll run one on CPU and one on GPU. That's on an NVIDIA GPU using RunPod. So I'm in the main branch of advanced transcription, and I'm going to work out of speech, text-to-speech. This repo has scripts that cover all 3 forms, so speech-to-text, speech-to-speech, and then text-to-speech. Also, there's a discussion of voice detection and turn detection, which I recently made a video of. So in text-to-speech, you can find scripts here on Mellow TTS, on Style TTS2. That's a diffusion model that you can fine-tune. There's scripts for fully fine-tuning that. But today we're going to look at Trellis CSM-1B and then Trellis Orpheus. So as I said, I'll start off with CSM and running it on my Mac here. And it's easiest if I just get started by going to the README. So first thing we want to do is install some requirements, and then I'll show you how to do some inference, and then I'll show you how to do voice cloning by providing an example of my voice and then cloning it. So I'm going to make sure I'm in the correct folder and install the correct requirements. I recommend using Python 3.10. You might run into issues with different versions. And now for basic speech synthesis, we're going to run CSM-TTS.py. Now, so you know, if you want to find this model, you'll be looking for Sesame CSM-1B on Hugging Face, and should be able to find the scripts here. And actually, there are some little code snippets that you can use if you want to build out these kind of scripts yourself. There's no code directly here on cloning, but there is on inference. Let me show you what the code looks like in full. So I'll go here to my basic script, CSM-TTS, and yeah, it's pretty easy to describe. I've got a loading function that's going to load the device to CPU. I think I might have tried loading it to MPS. We can try loading it to MPS, but I think it will fail. That's for Mac. And by the way, if you were going to CUDA, you would put in CUDA here. And then we're going to call the generator by passing in some text, passing in the speaker number, because CSM is trained to have speaker numbers. It's a fine-tuned model. And then we'll have a maximum generation length of audio, which is in milliseconds, so 10 seconds. So we're going to generate the audio, and then we're going to save the audio as audio.wav, and then we'll be able to play the file. So I'm going to run this here now. Let me just go back to my README, get the command for running. I should call that the bash command, and run it here from command line. And by the way, when I run this script, I'm just simply passing in the string hello from Sesame. So it's going to be a very short generation here. Now you can see the model is being loaded. So the reason why it's printing out here is because if I go to load CSM-1B, which is being loaded from the generator file, and this is a file that's provided by Sesame, in the model loading function, here's a loading tokenizer. Here's the definition of the generator. What we're interested in is the model. And you can see the model, it actually follows the syntax for Hugging Face. It's been loaded using from pre-trained with a torchd type of bfloat16. And I've just added in this line here to print out the model. I like doing that because it tells me what the model looks like. And unsurprisingly, it looks exactly like a Llama model. You have the backbone, which is the Llama model, embeddings, 16 layers from 0 to 15 that contain attention and multi-layer perceptrons, and then a norm and an output. And CSM-1B has got two transformers because it's got the hierarchical transformers. The first transformer decodes the very first or most important token of the hierarchy for that timestamp position or that segment. And then the next transformer will decode out the rest of the tokens for that position. So that's why you have the second decoder, which is a lot smaller. It's only 4 layers, 0 to 3. And yeah, it also has a Llama architecture. It's a 100M model, which I assume is initialized just from scratch because I don't think there's a public 100M Llama model available. So after that, and by the way, the model is 2.89 gigabytes, which is a little bit bigger than just Llama 1B because it's got that Llama 100 million model as well. And you can see here that actually there's an operation that's not currently featured for the MPS device. And that's the reason why I said I probably shouldn't change that to MPS. So I'm just going to rerun the script using CPU. It should work on CUDA though. So now I've reloaded the model and we're running through generate. And now we do have a file that's being generated. So it's this audio.wav file, which I can play now.
Hello from Sesame.
And yeah, it's a very nice sounding voice. The quality of data that this model has been trained on is really high. Now, that was a really short example. So let's go to one that's a little more elaborate and let's try to do some voice cloning. Now, the way voice cloning works is it's like instruction tuning in a language model. So in the same way, you might provide some few shot examples if you want to answer maybe some maths questions. You can provide some few shot voice examples if you want the accent to be replicated. And the reason why that works is because the later tokens that are generating are paying attention to the earlier ones, and that voice tends to be copied across. Now, this model here, CSM-1B, has also been fine-tuned for multi-turn conversations where I'm having a discussion with an assistant, and this notion of the speaker number is embedded within the syntax of how the prompts are being sent in and how the tokens are being sent in. So the model will expect there to be it will allow there to be a number of speakers. And if I pass in the turns of a prior conversation, it's going to continue with that same pattern. If it's got kind of revolving turns between me and the assistant, then it's going to expect my next accent, if I'm now the user again, to match the earlier user example that I provided within my long prompt. So I'll show you this within clone.py. We'll take a look. It's going to make use of audio files in the data directory, which I've added here. And it's going to clone a voice to generate new speech using the same voice characteristics. Now, what you can do to create the voice that you want to clone from is just record yourself. You can record yourself in M4A or in WAV. If you record in M4A, then just run this script here, convert M4A to WAV, and that'll convert it. Then you'll need to write the transcription of your voice. Use a transcription service if you want, like Whisper or something, and then adjust the text you wish to generate in clone.py. So let me actually just do each of those steps. I'll start off by making a short recording. Let me go to my voice recorder, voice memos here. And I've got voice memos open on another screen. I'm just going to record something very short. Greetings, my name is Ronan, and it's nice to meet you. So I've done that, and I'm going to get that piece of script. So I'm going to just copy the recording, and I'm going to go here to the data folder, and I'm just going to paste this in. So let's try to paste it into the data folder here. Greetings, my name is Ronan, and it's nice to meet you. So I'll just copy in the file here, and I've typed in the transcript here myself. I'm going to copy that because I'm going to need it. And I'm going to run this conversion script, uv run convert M4A to WAV. So it's taken in my script here. It's nice to meet you, and it's converted it into a WAV file, which we need to run clone. Now, if I take a look at clone.py, let's see at how this is being set up. So actually, I was running cloning on part of a song. It's a song called The Rocky Road to Dublin. So I had some transcripts in here and some phrases that I recorded myself. But let's just put in the example I have now, which is, it's going to be this greetings. So I'm going to copy the transcript from here, and then I'm going to put in the audio path, which should just be this here. So we have a transcript, we have an audio path, and what we're going to do is pass this in as context. Actually, it's going to be sent in as segments. So let's work backwards here to see how this is all put together. Basically, when we run the generator, we'll pass in the text to generate, which is, I'm going to put in a simple question here. How are you doing today? So this is the text we want to convert to audio. We need to specify the speaker that we're generating from. It's going to be speaker 0 because I'm only going to have one speaker in this conversation. And then we're typically going to pass in the context. Now, if you don't pass in any context, there's not going to be any voice cloning. So in this case here, we're actually generating a baseline where there's no cloning. Then in a second example, so we have the comparison, we're going to pass in text that we want to generate. And I want to pass in the same phrase of text. So I'm going to put in text to generate here. I'm going to put speaker 0, but now as context, I'm going to pass in the segments. And the segments are defined up here above. Basically, it's a combination of the transcript and also the audio paths that I've specified up here. So you can specify just short little transcript phrases and then short audio recordings for each of those phrases. So here I'm just passing in one very short snippet. And with that, I should be able to run uv run clone, and we should be up and running with running a cloning example. Now, when I run the cloning, it's going to save two files. It's going to save a first one that's going to be called baseline, and then it'll save another one called cloned. And in that way, I'll be able to compare what both of these sound like. And the output, I think, should be generated here, baseline and cloned. So we'll see it appearing now shortly. And there we go. So let's listen to baseline.
How are you doing today?
So clearly the baseline is not a clone because it's a woman's voice.
How are you doing today?
And by the way, if you run Sesame, it's going to have a random voice if you just generate without having any cloning. Because yeah, there's randomness injected in the sampling. And once it starts off on a certain voice trajectory, it's going to continue on that voice trajectory. Now for cloned,
How are you doing today?
let's do that again.
How are you doing today?
It's actually not bad. It's somewhat close to my recording that I provided for the cloning. So that's a very quick demo of how you can inference the CSM-1B model. Okay, so that's the cloning example. Now there's one more advanced version of cloning I want to show you, which is called context-aware. Well, I'm calling it context-aware generation. You see, the problem is when you use text-to-speech models normally, you're just generating a chunk of speech, but there's no knowledge of how that fits with the previous emotions in the conversation. And this is something that the CSM-1B model solves for because it's trained on longer conversational data. So you can actually provide in the previous parts of the conversation, not just the text, but the audio. And that allows you to get kind of a seamless conversation where you're flowing in a way that the AI sounds consistent between not just its own previous voice in the earlier responses, but also your own emotion as a human in engaging with it. And this allows you for a more engaging conversation. So I'm going to show you a more complex script here called context-aware TTS. Now, the easiest way to understand how this works is just for me to go ahead and show you a demo. Basically, it's going to ask me to read out a certain portion of speech, and it's going to take that as an earlier turn. It's going to provide an AI turn, and then it's going to get me to respond again, and then it's going to respond again with AI. So it's a multi-turn conversation, but each time I'm passing in the entire history, and what we should see is consistency in the voices as we go through. So here, run context-aware TTS. So it's now generating a first turn of conversation. It's creating the audio for this AI turn.
Hello.
And actually that has failed. So the audio that was generated was not valid. It should have generated audio here for this text snippet. And that failed and just shows you some brittleness in the model. So let's rerun it again. And to be clear, with the first generation, there's no cloning. It's literally just trying to generate an assistant's voice.
Hello, I'm an AI assistant. How are you doing today?
Now, I'm going to respond to that. And I'm going to respond saying, I'm doing well, thanks for asking. What can you tell me about voice synthesis? And then it's going to take the original AI question plus my response and generate the next AI response. And the voice should be consistent between the first and the second AI response. So let me just read this out. I'm doing well, thanks for asking. What can you tell me about voice synthesis? So now it's going to generate the AI response to me. And by the way, this is pre-programmed in terms of text. It's purely a text-to-speech generation that I'm doing. But what I'm trying to show you is how I can get an AI that has a consistent voice between the first turn and then the second turn and then any subsequent turns.
Voice synthesis has made incredible progress in recent years. Modern models like CSM can clone voices with very little data and maintain the speaker's style and emotion. It's fascinating how we can now have these more natural conversations with AI systems.
Okay, so that was the AI voice. It's hard to tell, but I'll play the full conversation later and you'll see the AI's voice is consistent between the two. Now, there's a human voice that's going to respond, which is mine. But rather than me saying this out loud, I'm going to use the prior turns and pass all three turns in order to generate this fourth turn, which will be a clone of my voice in the second turn. So we should hear that momentarily, and hopefully it'll sound a little bit like my own voice.
That's really interesting. Check this out. Just was on up to yeah, more up to camera. So systems actually work. Do they need a lot of training data, and how natural can they really sound compared to real human speech?
Okay, so I have to admit that was kind of poor in terms of quality. It basically skipped a lot of these words here. And then on the later words, it kind of caught back on track. So we're going to have a fifth turn here from the assistant, and we'll listen to the voice generated here. Should again be consistent with the earlier assistant's voice pattern.
Great question. Traditional voice synthesis required hours of recordings from a single speaker, but modern AI models like CSM can produce remarkably natural speech with just a short sample. The key is that they're trained on diverse speakers and can generalize voice characteristics. While they're incredibly good now, human speech still has subtle nuances that AI is getting better at capturing. The gap is narrowing every year, though.
Okay, so we have a 5-turn conversation that's been recorded. Now let's play all of that conversation just in a row with UV run, play conversation. Before I play the full conversation as one unit, I'll just quickly go through context-aware TTS and how this works. I'm in each case defining the text, and I'm generating speech from that text. Each of the turns is a call to the generate function. So you can look at generate. The very first turn is the assistant speaking. This is the AI reading out turn 1 text. So this gets a response, and then that response is added to a conversation history via a segment. So we create a segment, we add it to the conversation history. Then we call generate again. But actually the second turn, we're not passing in a recording. I'm recording my voice live. So it will move to this else loop. The human will record this, me recording my voice, and then my segment is appended on here to the conversation history. So we now have an AI response, a human recorded response. The next generate is then the AI again, reading out turn 3 text here, passing in the conversation history of the previous 2 turns. Then we move to turn 4, which is human generated. Well, it's a human clone voice. So it's my voice being cloned, passing in the full conversation history and the turn 4 text. And then we have turn 5, which is the assistant again. And this is passing in the conversation history with all 4 prior turns plus turn 5 text. So I'm just doing the cloning at each stage, passing in the full conversation history. And here's what all this sounds like if I run play conversation, which simply loads the 5 voice segments and plays them all. So let's have a listen.
Hello, I'm an AI assistant. How are you doing today?
I'm doing well. Thanks for asking. What can you tell me about voice synthesis?
Voice synthesis has made incredible progress in recent years. Modern models like CSM can clone voices with very little data and maintain the speaker's style and emotion. It's fascinating how we can now have these more natural conversations with AI systems.
That's really interesting. Check this out. Just goes on to yeah, more options can actually work. Do they need a lot of training data, and how natural can they really sound compared to real human speech?
Great question. Traditional voice synthesis required hours of recordings from a single speaker, but modern AI models like CSM can produce remarkably natural speech with just a short sample. The key is that they're trained on diverse speakers and can generalize voice characteristics. While they're incredibly good now, human speech still has subtle nuances that AI is getting better at capturing. The gap is narrowing every year, though.
All right, so you can hear the conversation is definitely flawed. The assistant reads out nicely what I provided. I record my voice. The assistant responds nicely. By the way, I've put a pause of 1 second between turns, so it seems like there's quite a delay there. Then the human cloning of my voice is actually flawed. It breaks up. It kind of recovers and comes to an Irish accent, although it's not matching my accent quite as well. And then the final assistant turn is quite good. So you can see here, there's definitely room for improvement in terms of how the model is handling this cloning, perhaps with more training data. So if you trained it more on my voice, you would avoid those issues. But you would like to think that even without doing a lot of training, this cloning should ideally work a bit better. And so that is the overview of the CSM-1B model. I'll provide some links below to the original scripts that are provided within the model card and also within GitHub. Next up, we're going to move to Trelis Orpheus folder here and run the Orpheus model. Now, for the different parts that I'll cover in Orpheus, which are namely inference, cloning, fine-tuning, and then the combo, I'm going to show you the inference and cloning in Google Colab. So I'm just going to upload these notebooks directly to Colab, and I'll make them publicly available as well. And then I'll come back here within Cursor, which is hosted now on a RunPod GPU. I'm going to show you how to do the fine-tuning, the data preparation, the fine-tuning, and then we'll do some inference of the fine-tuned model. So I have here the inference notebook and the cloning notebook, and I'm just going to run through these. So to start off, I'm going to specify the Orpheus fine-tuned model. There's also a pre-trained version. So there are 2 versions from Canopy Labs, the fine-tune and then the pre-trained. You can find them both here. And I'm going to set the device to CUDA, and I'm connected to a T4 GPU. I'll make sure I install everything here, and then I'll connect to Hugging Face. Now you do need to connect to Hugging Face because these are actually gated until you accept the terms and conditions. Now, once I'm logged in, we're going to load the tokenizer. It's the snack tokenizer that I talked about earlier. And then we're going to load the Llama model and specify the path for what we want to download. And once everything is loaded, we'll be able to specify the prompts, and then we'll be able to format the prompts into the correct template and generate the output. And I'll go through the code in a little bit of detail later on. Okay, so with the install done, I'm going to need to set a Hugging Face token. You can run this login from Hugging Face, but if you're having issues with widgets, you can instead just pass in a token here as a password and save it to token, which I've done there, and you can get a token from this address here. And once I've entered that token in, I can just set it in the environment. So HF token is set, and I've downloaded the SNAC model now, which is used to convert audio into tokens. Now I need to download the tokenizer and the model itself for the Llama model. Now it's not raw Llama, it's the Llama model that's part of Orpheus. So we will use snapshot download, and note that this won't work if you haven't specified your token because it's gated and you need to provide authentication in order for it to access it. So the model is going to download, and then we're going to pass in prompts. I'll just pass in this prompt here from Tara, and you can choose one of the voices. So this fine-tuned model is fine-tuned on a few different voices, and quite simply it passes in a string for that chosen voice. We'll see that when the prompt is templated, and that's just how the fine-tuning works. So that when it sees the word Tara, it's gonna know to use the voice of Tara. It's a bit like LoRA fine-tuning. When you're creating images using diffusion, you'll often put a little tag in the prompt that says Ronan LoRA or something, and because you fine-tuned with that tag, when you use the tag in inference, it's going to use those attributes. So the model is still loading. We'll take a look at the prompt formatting here. I'm particularly interested in seeing where the chosen voice gets passed in. And quite simply, in the Orpheus model, the chosen voice is prepended to any prompt with a colon and then a space. And we'll see this when we fine-tune the model on my voice. We're going to have prepend in Ronan, followed by a colon and then a space. So all of the prompt tokens are being converted, or all of the prompt words rather, are being converted into tokens. And we have a start of human token being added in, then an end of text and end of human here. So this is how the template is working. And basically all of the prompt is going to be templated in this manner. We'll see later in cloning where we'll put in previous turns, but for now, it's pretty simple. We just have one prompt. It's going to have a start of human token. It's going to have end of text, end of human. And with the templating done, we have a little piece of code here to generate the output IDs. We have a standard generate function here. And once those tokens are generated, we're going to convert from tokens back using the SNAC tokenizer. So you can see back down here, we have the SNAC model that basically converts the codes back into audio. And notice that because this model Orpheus, it's actually generating a sequence of tokens for each segment of audio. When that sequence is generated just in a long sequence, we need to take them in groups of, I can't remember how many tokens there are, maybe it's 4 per segment. We need to take those and put them into little mini groups, because each mini group is then decoded, because that's the full hierarchy for that segment position. So this is what's happening here with the redistribution. Once we generate a long sequence, we're redistributing them into little groups, and those little groups then are being decoded using the SNAC model into audio. And then we print the audio and we can see what that sounds like. So meanwhile, the model I think is being downloaded. We can set the prompt. We can format the prompts into the tokens, and we can generate some output. And then we'll parse the output as speech. Now this is quite a short sentence, and we are on GPU. So even with the T4 here, the speed is not excellent. Note that this is using model.generate, and VLLM should be quite a bit faster for doing higher speed inference. So we've got the token IDs generated, and now we will parse those, so organize them into little groups and decode them using the SNAC tokenizer. And then we'll be in a position to just play this little piece of speech here. So here's the speech.
Hey there, my name is Tara. And I'm a speech generation model that can sound like a person.
Okay, so that sounds good. And notice how there are these kind of special tokens. They're not actually tokens, but they're strings. And these represent certain non-speech elements of the recording. And what Orpheus does is have a base of training data that has chuckles within it, and then they will place within the transcripts the word chuckle. You can have different versions like laugh or giggle, or I'm not sure exactly which ones have been tuned, but this is a way to introduce non-speech elements, which is pretty nice within your pre-training data set. And that's something, or rather your fine-tuning data set, that's something you can do as well when we go to fine-tune. So this is an example of just running straight inference. And now I'll move over to cloning here and connect to the T4. Now I will want to do the login here, and I'm going to log in, use the token so I don't have any issues with the widget. We're connected. I'm going to use the pre-trained model for cloning, so we're not going to use the fine-tune because I don't need to access Tara's voice per se, so I don't care that the model isn't fine-tuned for Tara. And I'm going to enter my token now, which I should get from this address. So we just go to the tokens, and I'll enter my token here and set it as an environment variable. And now we're going to be running, we can run here using pip, just do all of those installs, enable HF transfer. By the way, this is another way you can log in. You can use interpreter login. It tends to run into less widget warnings as well. So that's another option I'll give you there. And then we're going to do the exact same things. We'll define the device as CUDA, download the tokenizer from the Llama portion of the model, of the Orpheus model, download the snack model, and then we'll download the Llama model itself and move it onto CUDA as a device. Now, next we're going to move to doing the cloning itself. And for the cloning, we're going to need an input file, and we're going to need a transcript. And the input file I've pre-recorded, you can record your own, is simply me saying the words, this is how you count to 3, 1, 2, 3. And then I'm going to try get the model to continue on and say something like 4, 5, 6, 7, 8, 9, 10. So I do need to upload a speech file here. And I'm going to do that by going to the files and upload. And in the advanced transcription folder in text to speech, underneath Trelis Orpheus, I do have this file x.wav. So I'm just uploading that file now. In the meantime, we should be doing the installs. It looks like that's progressing. And now, once I have this here as an input audio and a transcription, this is going to get passed in as the prior conversation. And then we're going to continue onwards from there. So now when we tokenize, we're going to tokenize not just this text that we want to convert to speech, but we're also going to tokenize the audio and the transcript that we want to pass in. So we have a function to tokenize the audio, and then we're going to append the start tokens, the end tokens, the final tokens, and we're going to create our voice prompt here. So pretty much a similar setup to before, but we're going to be tokenizing not just audio, but also tokenizing text and putting it all together as an input to the model. The generation function is going to look very similar here. We're going to convert the output then to speech with the help of our snack tokenizer, which should be right down here. And then we'll display the speech and we'll see how the voice cloning does. So we're just downloading the snack model now, and we're moving on to download the Llama model, or the Llama portion of the Orpheus model rather. And this model is a bit bigger, by the way, because we're using a 3B backbone. So if you have that in 16 bits, that's going to be 8 bits per byte. So there's going to be 2 bytes roughly for every model parameter. So you have at least 6 billion, at least 6 gigabytes. It's actually a little bit more that you need to download in model weights. And just while I'm waiting for the model to download, if you're running this locally, you can also just run this short script and record. What it will do is allow you to record a snippet of audio. You will basically just start recording, read out this phrase here. This is how you count 3, 1, 2, 3. And then it's going to save that as x.wav. Now, it's a little bit harder because you have to manage microphone permissions if you're doing that from Colab. You could adjust the code in order to do that, or just upload an audio file like I did, which I have here now, x.wav, and we should be ready. Okay, so the model has been loaded and we're ready to run the inference. So I'll just define this input audio file, get the tokenization going, and then start to run the inference. And after inference has been run, we'll convert the codes back to speech by grouping them and then converting the codes. Now, just a reminder, the Orpheus model is just a single transformer. It produces all of the tokens just in one stream from that transformer. There's no hierarchy of transformers like the CSM-1B model. So just maybe under 30 seconds to generate the speech. And now a little bit of time to decode. And now we have the speech ready and we can listen.
4, 5, 6, 7, 8, 9, 10.
So that's supposed to match my voice. You can think of me saying 1, 2, 3,
4, 5, 6, 7.
It's maybe not a bad representation. I would say it's not perfectly matching my voice. So we're going to take things a step further. And next we'll move to fine tuning on more examples of my voice, many more examples actually, to see if we can get closer in terms of what we get with the voice match. Now, I suppose just a few conclusions from this quick cloning test. You can see that inference speed is an issue for audio, and that's just because there are quite a few tokens that need to be generated. For every second of audio you have, if you've got, say, that frequency of 12.5, like for CSM-1B, you've got 12.5 times the number of kind of hierarchy tokens at that position. So you need a lot of tokens being generated per second in order to keep up with real-time voice. So that's it for these demos here in Colab. I'm next going to move to back to Cursor and run the fine-tuning, data generation and fine-tuning using the scripts in the advanced transcription repo. Next, we're going to look at fine-tuning Orpheus, and then I'll show you how to combine it with cloning, which gives really good results. So fine-tuning requires 2 steps, data prep and then fine-tuning. I'll show you fine-tuning, full fine-tuning of all weights, and then fine-tuning with LoRA if you want to save memory. Actually, the full fine-tuning performs better for me, although maybe if I used more data, the LoRA would work similarly or possibly better. So there are 2 steps. I'll walk you through the data set prep, and then I'll walk you through the fine-tuning itself. I'm going to do the data prep on my local computer, and I'm going to do the fine-tuning on a remote GPU. Now, earlier in the video, I started with a 48 gigabyte VRAM GPU, but actually, if you want to do full fine-tuning, you need to have probably 80 gigabytes. That's because it's a 3 billion parameter model, and 3 times 2, because it's in 16 bits, that's 2 bytes per parameter. That means the model needs at least 6 gigabytes to be loaded. Actually, it needs a bit more. But if you use full fine-tuning, you also need 4 bytes per parameter for the optimizer, and you need 2 bytes per parameter for the gradients. So you will easily run out of VRAM if you just use an A40 that has 48 gigabytes. So I've actually started up an H100 SXM with 80 gigabytes of VRAM, which will allow me to do full fine-tuning. If you want to use a smaller GPU, like if you want to use Colab, you can do that. Just use the LoRA fine-tuning then in that case. LoRA fine-tuning will take you probably under 10 gigabytes, definitely under 12. So it should fit fine on less than 16 gigabytes if you're going to use, or 15 gigabytes if you're going to use Colab. So here we go. With the data preparation, I'll open up a terminal, make sure I'm in the right folder, make sure I do some correct installs. Now, I'm not in the inference section. I'm not in voice cloning. I'm in fine-tuning, and we're going to use UV to speed up installs. So let's move into the correct folder and install the requirements. I'm not actually in the right folder there, so that was a mistake. I need to first move into the text to speech folder. So let's try rerunning that. And it's not finding requirements because I'm still not in the right folder. That's because I need to be in Trelis Orpheus. Okay, installs are working well, and I'm not going to install Flash Attention just now because I'm running locally and I'm just doing data prep. What I'm going to do is record a data set with just 4 examples of me talking, and then with the transcripts. The way I'll do this is by writing out words that I want to speak in advance. So I'll have 4 different phrases and then I'll read them out. Actually, you want to generate more samples, probably at least 50, but ideally maybe 250. I've created a script here in the fine-tune folder for doing that. It's called record voice dataset. And I've just got an AI to create some examples of sentences of different types: basic sentences, technical, conversational, some questions. Questions are key because the assistant might want to ask you questions. Some emotional ones to cover different emotion ranges, and then some long sentences as well. Now, I have recorded all of those as a data set, but I'm not going to do all of those now. I'm just going to record 4 to keep this a little bit faster. Now, the data sets I'm going to generate, let me show you what they should look like. I'll go to Trelis Orpheus FT to show you an example of a base data set. Here I have 18 rows. It's actually the 18 rows, the samples I just showed in the script. We have the text, the source. This is my name here. Eventually, this is going to get prepended with a colon into the tokenized data set, and then the audio. So this is a data set you could use to train any model. It's not in a specific format for Orpheus. But then we're going to run an other script that will convert this into a formatted data set that looks like this, which has got input IDs. It now does include Ronin colon. It does include start tokens, end tokens, labels, and then the attention mask. So this is the formatted data set, and I'll show you a script to tokenize to get this data set. And this is what will be fed in to either the full fine-tuning or the LoRA fine-tuning. All right, so everything is installed and we're ready to create a few examples. The test flag here indicates we're just going to create 4 rather than using the full set of examples. And this here is the name of the data set I'm going to push to Hugging Face. And here I can just run this script. So I'm going to run, and it looks like I am missing port audio. And that's because this here is remote and I said I would run this locally. So let's run it locally. Let's use my Mac. I should use my microphone, but I don't want, in case it's going to break my recording here for YouTube, I'm going to just run it on Mac. So I'll press 5 and okay, let's get started. The weather today is absolutely beautiful. The weather today is absolutely beautiful. So I'll keep that. Blockchain technology offers a new paradigm for secure transactions. Blockchain technology offers a new paradigm for secure transactions. Sorry, that's terrible. It's AI generated, so we've got some pretty terrible phrases. Let's keep it though. I'm not sure about that. What do you think? I'm not sure about that. What do you think? And yes, to keep it. Last one. I'm so excited about the upcoming concert this weekend. I'm so excited about the upcoming concert this weekend. Now, if there's one criticism I'll give here, it's that when I record these, there's probably a little delay at the start before I start speaking, and you might want to trim that. You might also want to record examples where it's like follow on. So you have an AI speaking and then I record myself responding just to get the natural timing that there should be between turns of conversation. So that data set has been recorded. It's failed pushing to Hugging Face because I haven't logged in. I should do that using Hugging Face-cli and then log in. But I'm not going to do it because I don't want to overwrite the data set that I've already pushed and that is up here. It's the data set here that is not formatted. So I have this data set I recorded earlier with 18 rows, and now I do want to format it. So I'm going to move down in the script here, and I'm going to go to the section on tokenizing. So I'm going to run, by the way, if you fail to push after recording, you don't have to re-record. You can just run this push raw dataset script and specify the speaker and specify where you want to push to. But next we're going to tokenize, and to tokenize, we need to make sure that the snack library is installed because that is used for tokenizing audio. Make sure you're logged into Hugging Face, and then you can run this script here. I'll run it here, and in the meantime, I'll just explain that the input dataset needs to be specified and the output dataset to tell you where you want to push. You can see this failed because I specified doing it with CUDA, but I'm on Mac. So if you want to run on Mac, you need to run it with MPS, or you can run it with CPU. So I'll rerun that there. If you're on CPU, then you can run with CPU. So let me just save it still with CUDA as default. Here you can see it's downloading. It's downloading from Hugging Face, and it's currently failing to push again because of Hugging Face. Let's actually just fix that issue now. I'm not worried about pushing again because the data set it's pulling from is the actual one I want to use. So here we will grab a token, enter this token, and now rerun that script. So it's fetching the data set that's unformatted, loading the tokenizer, processing the 18 rows, saving that, and now it's going to push up to Hugging Face. Now, you can also check that the data set is valid and there. This is a good idea. Just UV run, and then this here, we're going to check, and it's going to tell us whether the data set exists at that location and also whether what the structure is of the data. So everything looks good here. I've run check data set. So I've got a data set and I'm ready now to fine tune. I'm going to fine tune on a GPU. So I'm going to move over to my GPU here. This is where I'm running advanced transcription on the H100. And to do the fine tuning, we need to set up a config file. And that config file will serve for full fine tuning, but also for LoRA fine tuning. Now I'll show you the config file in a second. But first, let's maybe get the installations going and the script going. So we save a little bit of time. We're going to make sure that we're logged in. And I don't think I'm logged in. So I'm going to run this command. And I can't run the command until I install Hugging Face Hub. So I could just do uv pip install Hugging Face. Can I spell that? Hugging Face Hub. And now I can probably log in and uv run Hugging Face. Need to fix my README here. And again, get a token. And I'll just invalidate and refresh. Copy that token and make sure I'm logged in now on the GPU. And I'm going to run the installations, but this time I'm going to install Flash Attention because I'm running on GPU. NVIDIA will support the Flash Attention library here. I'm going to use TensorBoard, by the way, for logging. I'll show you that in a moment. And with the installs done, I'll be ready to train. But one thing first, which is I need to set up the configuration for devices. This actually would allow you to run on multiple GPUs, at least for full fine tuning. You would need to make a few tweaks to the LoRA script to work on multi-GPU. But we're going to run accelerate config, and we'll just tell the config or set up in the config that we're just going to run with one GPU. And we're going to run with mixed precision. We're going to run in BF16, BrainFloat 16. So we'll also set that up in accelerate config. So I'm going to run config now. And once this is specified, we'll be able to export an environment variable for fast weight downloads and then run the training. Or alternatively, we can install PEFT, parameter efficient fine tuning, and run train LoRA here, which will be a LoRA version of the training. Now, while we're waiting on that script here for the accelerate config, let's take a quick look at the configuration file, which is in config.yaml. We've got the data set, which is formatted. We've got the raw model. We're not going to use the fine-tune model. We're going to train for one epoch, batch size of 1, just one process because it's one GPU on one node. The pad token for Orpheus is this one. Save steps if you want to save intermediate copies of the model during training. If you set it to something really high, it's just not going to save during training, which is fine. The learning rate will be 5e-5. That's what Orpheus recommend. The scheduler will be constant. I like constant rather than cosine. If you want to do some kind of decay, you can do a little bit more training at the end with a cosine or linear decay. I'll specify the save folder, the project name, and then the run name. Notice that I'm using the training learning rate, the number of rows, the number of epochs, and then the scheduler type of constant as the run name right here. Okay, so this is the config file. Let me quickly show you the training files. First, we've got the train.py, which is full fine tuning. It will load all of the configs, load the data set, and pass all of those into the training arguments. We're going to use an eval strategy here of epochs. So we're going to evaluate every quarter of an epoch. Notice that to do eval, I'm going to create a an eval split. And the eval split is set up to have a minimum of 1 example, a maximum of 25, and a default of 10% of the total rows. So if we've 18 rows, it's going to create, I'm not sure about the rounding, I'd have to read it carefully, but roughly 1 or 2 eval rows. So that's the training arguments. We are then going to pass those into the trainer with the model and the data sets, and then we'll train. And at the end, we're going to save the model and save the tokenizer. Pretty straightforward. For LoRA, it's all the same, except we're going to apply LoRA adapters. We'll apply them with a rank of 32. We'll set the alpha to 64. And you can see here that we apply LoRA to the attention modules and also to the feed forward, which are the MLPs. And we're also going to fully train the LM head and the embed tokens. This will take a little more memory, but it generally gives better results. And we're going to use rescaled LoRA. This is basically a way to kind of automatically set the learning rate for the adapters the adapters should always be trained at a higher learning rate because they're operating in lower dimensions, which means you can move faster along the operation curves. So we set up the LoRA, get the model, basically apply the adapters to it. The training is all the same then. We still use an eval split. But then after training, we have to merge the model. So we have this line here to merge the adapters onto the model before we do the final save. Okay, so that was the two training scripts. We're going to finish accelerate config, which by the way will be the same for LoRA and full fine-tuning. We're going to train on this machine. We're not going to use distributed training. We're not going to train on CPU. We're going to use the GPU, and we'll use the defaults not to use Torch Dynamo, Deep Speed. We're going to use all GPUs, just press enter. And we're going to default to known Llama efficiency. Don't really know what that is. And we're going to use mixed precision BF16. And I think we're in good shape now to run this training. So let's run the script here. Hopefully everything should work smoothly, and then we can start up TensorBoard. So here, actually, it will be smarter if I move the install to happen within the folder, because the UV environment is actually inside the fine-tuning folder. So while this script is starting up, let's create a new terminal. And this is going to be for TensorBoard. So we're going to move into the fine-tune folder, use UV to install. The virtual environment is in the fine-tune folder, and then we'll run TensorBoard. So TensorBoard should be up and running. It shouldn't display just yet because training isn't started. For that, we need to wait on some downloads. You can see, first of all, we have a tokenizer being downloaded. You can see we're downloading the model now, which is about 5 gigabytes in size. Sorry, no, it's much more. This is just one shard. And by the way, the model is saved on hub in 32 bits. So it's actually not even roughly 6 gigabytes. It's roughly 12 or more. I think it's actually even over 15 gigabytes. But then in 16-bit, it would then be closer to 6. It's a bit bigger than 6. Okay, so with the fast weights download, we downloaded the model fairly quickly. Actually, it's about 5 and, very roughly 15 gigabytes in 32 bits. The model is now loaded. We've got our training split, 16 training, 2 eval examples. And now we're starting to train, and it's really fast. It's really fast because the model is just really small. So you can see the loss is falling here, which is good. And if we check out our TensorBoard view, we can refresh and this should show up here. So yeah, we can see our training. We have the grad norm. It's a little bit high, to be honest, which suggests you might want to try out lower learning rates. I did try lower learning rates, didn't really get better results. So I think this is probably okay. If you want, you can maybe turn on some smoothing if you want to kind of see what's happening, some serious smoothing. You can see a rough indication. Maybe it's better sometimes to just look at the raw data. The training loss is falling, so this is good here. And yeah, basically the training should be complete and we should be able to examine what's happening. And with the training done here, the model needs to be saved. It's going to be saved inside the checkpoints folder here. So you can see there is this checkpoint 16 corresponding to the last step of training, step 16, because we're using batch size of 1. You can use a larger batch size, but you do need to adapt your script because you need to pad the sequences to the same length. So currently I'm not padding the sequences, and that's why I'm using just a batch size of 1, but you do need to pad out the sequences if you're going to use a batch size larger than 1, which, by the way, can sometimes stabilize your training, reduce your grad norm, which can be good, provide smoothing. On the other hand, it allows the model to learn less specifics from each of the samples. So there can be pros and cons. And the model is now saved, so you can see it here. And we have our final set of logs here for the full fine-tuning. Now, you notice here that actually all of the logs didn't display until the script was finished running. So we can now see our eval loss as well. And the eval loss is just being calculated at one data point here, which shows you maybe we should be trying to evaluate a little bit more often. But we do have an indication that the training loss is falling. So we're going to go ahead and we're now going to do LoRA fine-tuning in the same way. So let's just go back here to the README and let's make one change here in the LoRA fine-tuning script. I'll search for the 0.25 and let's adjust this so that we have the eval steps a bit more frequent. We'll do it every 0.125 steps, which will be every 8th. There are 16 steps, so this should do it every 2 steps. Just give us a bit more eval data. And now we can run the LoRA fine-tuning. So let's go down to the script here. We need to install PEFT, and then we can run. So LoRA fine-tuning should now start. And note that it will append -LoRA to the run name. So that will distinguish it both in the logs and also when we save. Now there seems to be an issue here. Oh, that's because I've run again on my local computer rather than running on remote. So actually it's here where I want to run the train LoRA script. And you know what? That means this is the problem if you've got 2 terminals open that look the same. It means we actually need to update the config file to be here. So instead of 0.25, and it's not the config file, it's here for LoRA, I need to update to 0.125, 0.125. You could argue I should move some of these to be defined in the config. That would be a good argument. But for now, they're defined there. So I'll rerun the script. PEFT should install fairly fast. And then we should get started on this train LoRA script. Okay, so we're training with a constant scheduler here. Now using LoRA, we can see the run name is appended. Sorry, LoRA is appended as a tag to the run name and also to the model output file. We're going to load the checkpoint shards. And this error should be fine because we're using accelerate config for launching the script. The model now should be loaded. And we've got the same data set, 16, 2 for eval. It's running really fast here. And you can see the loss is falling. And it's then going to merge the model and it should save it. We can see some of the updates here, although the updates won't fully propagate until the script is fully finished running. So you can see the training loss is falling. The loss is a bit higher though than in the full fine-tuning. So you might think, well, maybe we should expect the results would be better from the full fine-tuning because of that. The grad norm is quite similar. Now keep in mind that we're training the embeddings, so that should make the LoRA training quite a bit more similar to the full fine-tuning. So we don't expect too much difference, but clearly there is some difference here. You could also argue the training loss is still falling, so you should maybe continue to train for more epochs. And that's basically where it's going to be useful to look at the eval loss to see if the eval loss is still falling, because if it is, that's a good indication that you should probably train for more epochs. So it's saving the merged model. That's going to be saved to the outputs folder right here. We have the fully fine-tuned model, and now we have the merged LoRA fine-tuned model. You can see here there are the shards. So it's taking 3 or 4 shards for saving the model in each case. It's interesting that it creates 3 shards in one case and 4 in the other. I'm not quite sure why that is. It might be on the threshold of being able to fit it into 3 shards, which I guess it is because it's around 15 gigabytes. So the model is now saved and the run is finished, which means we should be able to visualize the data here on the LoRA fine-tuning too. Now, it seems not to be displaying every one of my eval points. I'm not sure if that's because eval is not running. Yeah, the eval loss seems only to be run at that increment. Okay, so I'm running again here and I've just made a change. I've changed the eval strategy to steps. And when you set that steps in this to 0.25, then it's going to run at 1/4. It's going to run eval at 1/4 of the total steps that are configured for training. So with this, we are running now with LoRA, and you can see the updated results appearing here beside the full fine-tuning. The LoRA training loss is higher, as we saw before, but we now do have an indication of the eval loss. You can see that's falling, which is good. And when this finishes running, we'll have a better indicator of whether we're still dropping by the time we get to 1 epoch. Okay, the training is finished now for LoRA. And actually, what you can see here is that the eval loss between the full fine-tuning and the LoRA fine-tuning, it's very similar. The full fine-tuning is only slightly lower on eval loss. So this kind of suggests that even though the training loss is lower on full fine-tuning, it may just be overfitting. Whereas the eval loss here for the eval loss here for the LoRA model is pretty much the same. Also, you can see the eval loss is still falling, although it's falling fairly slowly. So probably you could get even better results than what I'll show here if you just train for more epochs. Arguably, you could also increase the learning rate a bit more. I know that the grad norm is high, but it doesn't seem unstable. The eval loss is falling nicely, so probably you could increase the learning rate as well. All right, so with those models trained, the fully fine-tuned and the LoRA fine-tuned, let's move to inference those. Just briefly, if you want to push the models to hub, you can scroll down here to the pushing to hub section and just run UV run push model to hub. Put the path here to the locally saved model, and then put the ID of the repo you want to push to, and optionally add in a flag for private here. Now, I'm not going to push the model. I'm going to focus on inferencing the model. And to run inference, I've got a simple inference script here, which is just Python UV run Python inference.py. It'll load the model, and it's going to run inference then on a specific prompt. And the prompt is, this is a test of my fine-tuned model. So let's test out the fully fine-tuned model, and then we'll test out the LoRA fine-tuned model and see how they compare. So this first is running the fully fine-tuned model. It's going to load it onto CUDA, onto our GPU. And for some reason, it looks like we don't have Snack installed, and that's because we did the dataset prepped on a different GPU. So, well, rather, I did it on my Mac. So UV pip install Snack, and then I can run again. By the way, it is critical to pass in speaker Ronan, because this will prefix any of the prompts with Ronan :space. And that's important because that's how we fine-tuned it. So if you don't pass that in, it's not going to know to speak like Ronan. And actually, this shows you as well, you can't really fine-tune with just one or two examples, because probably the model is just going to say the word Ronan : so it's only with more fine-tuning that it will know. This is actually a tag. It's not something you say. It's a tag that's indicating that the following words afterwards should be spoken with the voice of Ronan. So we've loaded the shards. You can see the model here. It's a single transformer model. You can see the feed-forward layers and the attention layers that we trained. You can also see the head and the embed tokens that we trained, both in full fine-tuning and LoRA. And we should now move to the generate portion of the script. Of course, we're running inference.py here. Looks like we're loading the Snack tokenizer. So here is the prompt we're running on. And we've generated the speech at fft.wav. Now I'm going to do the same for LoRA, and then we can start to play them. In fact, while that's running, I could just go up here to fft.wav, and we can try to play that script. And actually, we didn't output anything there that time, so that's a problem. Let's see if we get any better result from the LoRA model. So here's the LoRA.
This is a test of my fine-tuned voice model.
Okay, it still sounds a bit American, but it does maybe have some attributes of me.
This is a test of my fine-tuned voice model.
And as I said, probably training for more epochs, also using more data would get a better result. We can check the full fine-tuning here. And that has just failed. We can try to run again using full fine-tuning. And because there's sampling parameters here, there will be randomness in the generation. It's possible if I just run it again, I'll get a good result. Of course, this is really problematic if you're trying to run in production, because you can't rely on having an output being generated. So that is a big issue. And perhaps we're just seeing some overfitting of the full fine-tuned model. Let's see if it does any better this time. Okay.
This is a test of my fine-tuned voice model.
Okay, so that's the fully fine-tuned model.
This is a test of my fine-tuned voice model.
And yeah, I mean, this one sounds more American.
This is a test of my fine-tuned voice model.
And this one here, the fully fine-tuned.
This is a test of my fine-tuned voice model.
Yeah, it's in some ways maybe a bit better. It says tuned instead of tuned, which is very American. But
this is a test of my fine-tuned voice model.
Yeah, not too bad. So what I'm going to do now is try and combine voice cloning with the fine-tuned model. So we're providing some a one-shot example, plus we're using the fine-tuned model and see if that combination does well. So you can think of this script running inference this time with a one-shot example. It's called clone inference, but you're able to run it on any model. So we can take a quick look at how that script works. It will also kind of explain how the inference scripts work. But basically, after parsing the arguments, we need to load the model, we need to load the tokenizer, and then load the snack model. We need to tokenize the audio, which means we need to create tokens for each segment, and then we need to flatten them into one long sequence. Then we format the text. Note that if we define a speaker, if we pass in a speaker, then it's going to be prepended here, Ronan, colon, and then space. Then we will format the text, the reference text, and we'll also need to format the reference audio path. So we're basically putting together everything, the text for the audio, and then the text that we want to generate. And this is all going to go into one prompt that will then finally go to the generate function. So that's been done here within the generate speech function. And then once we generate the output tokens, we decode back using the snack tokenizer. Okay, so to inference this now using voice cloning and the fine-tuned model, I've installed Librosa, Torch Audio, and now I'm going to run inference using the clone inference script. I'm going to point to my fully fine-tuned model. I'm going to use CUDA. The reference audio is going to say this is how you count to 3, 1, 2, 3. And the prompt I'll give is, well, here I've got, let me continue where you left off. But actually, I think it would be better to just say 4, 5, 6, and 7, 8, 9, 10. So 6, 7, 8, 9, 10. And I'm going to want to do the same then when I use LoRA. So I've got the very same thing here, but I'm passing to LoRA instead. And here I'm going to save to an output of cloned FFT model.wav. Whereas here, I'm going to create a file of cloned LoRA model. So we should be able to compare then the performance in both cases. And notice well that I'm passing in the speaker. This is important because we want to prepend each of the prompts with the word Ronan and then colon, because that's how we've trained. That's how we've prepared the data when we tokenized it for the data set we pushed to Hugging Face. So you can see we're just loading shards of the model, and it's going to try and read out the rest. And it should also play the audio, I think, once it's done. Actually, we're on SSH, so it's not going to play it, but we can play it ourselves. In the meantime, I'm just going to run this script here for LoRA. And here is the FFT. So let's see how this is.
4, 5, 6, 7, 8, 9, 10.
Okay. So, I mean, it's not too bad. The way you can think about this is you can play first the X file here, which is just me speaking.
This is how you count to 3. 1, 2, 3. 4, 5, 6, 7, 8, 9, 10.
Okay, it's not bad. There's some kind of turn in the voice that I think is not characteristic of my own voice, but it's not a bad representation. We can try now LoRA. So still waiting on LoRA to finish. And it looks like LoRA is now being created. So let's do the same thing. We'll play my voice.
This is how you count to 3. 1, 2, 3.
And then cloned LoRA.
1 and 4, 5, 6, 7, 8, 9, 10.
Okay, so actually LoRA in this case was not perfectly reliable. It's got some kind of noise voice
1
here.
and 4, 5, 6, 7, 8, 9, 10.
And notice that it's actually saying the Ronan at the start.
1 and 4.
Which is not correct, because if it was properly fine-tuned, it would know that's just indicating how to speak. It's not saying that you should say those words. So this is a kind of classic problem here. If you don't train on enough data, probably, or if the model fundamentally is not seeing a lot of data examples of where it's been fine-tuned. And indeed, this is a base model that we're training. maybe if I trained the fine-tuned model instead, it would be better able to perform on this basis. So perhaps that would have been wise in my config. Instead of using the pre-trained model from Orpheus, I maybe should have used the fine-tuned model right up here. But we'll just give it one more go. Here we've the FFT model, and it looks like it's actually even failed to generate properly that time. So we'll try again. So the checkpoint charts are loaded, and we'll do this last inference here. Reference text, prompt text, and we'll try playing.
Ronan 4, 5, 6, 7, 8, 9, 10.
Yeah, so you can see here, it's saying Ronan very clearly.
4, 5, 6, 7.
So the results in this case seem to indicate the fully fine-tuned model is doing better. And maybe it's just because it has more parameters that are able to fit this pattern a little bit better. The LoRA model, I think, is doing okay if you use it in a non-cloning setting, but in this cloning setting, it seems definitely not to be picking up to the fine-tuned guidance around setting that speaker tag. And so this is an overview of using transformer-based TTS models. I think we're in the early innings, as they would say in baseball terminology, around these types of models. In a sense, I feel it highlights how in open source, the multimodal models are probably at least a year behind what's in closed source, because GPT-4o, that came out, I think, around summer 2024, which is less than a year ago now. But that means probably they had higher level of capabilities around this time, about this time last year. I think it's pretty important to understand how all these architectures compare, and hopefully I've clarified a bit how a pure text model compares with these now multimodal models. And hopefully I've given you some tools as well to fine-tune these models, which I think are quite a bit easier to handle than those like Style TTS2. You can find all of the materials in the advanced transcription repo. That's trelis.com/advanced-transcription. I've put quite a few links below to repos and to the scripts I've made available for cloning and inference for this Orpheus model. And you can let me know any questions below in the description. Cheers, folks.